Hey guys, welcome to another YouTube video. Today we're going to talk about the response, the overwhelming response actually that we received from yesterday's post about the high horsepower bolt-on applications that TurboDirect are designing for 2020. We spoke a little bit about some of the local tuners and tuners in general that are doing hybrid upgrades for certain vehicle brands. And after the post of the video yesterday, we were flooded with emails, calls, WhatsApp messages from some of the clients who are currently using the hybrid turbochargers on specifically the IS38 engine. For those of you who don't know what that is, it is the Golf 7 and Golf 7.5R engine, which uses the IS38 turbocharger as a standard component. That is the rotating assembly of the IS38 standard compressor and turbine. We'll get into that just now. So a lot of clients started calling us, tuners, fabricators, clients, end users, etc. started calling us and saying, listen, I've got this hybrid turbo on my car, built by this one, that one, the next one. Is it reliable? And the answer is no, they're not. We need to respond to all of these things, so we decided to make a video. Now, wherever there's a debate or a disagreement or critics or naysayers or haters, which you're obviously always going to get, that bring up certain things and start spreading rumors, etc., we go back to facts. We don't spread stories, we don't spread opinions. That's another reason why these videos are as raw as they are, is because we don't doctor anything to try and get a point across. Now, back to facts. We have failed IS38 turbochargers in various hybrid built guises on hand from the different tuners around the world, not just the local guys. This is not an attack on anyone local. This is not an attack singling out any company or any upgrade or any product or any name or any person. This is talking about a hybrid upgrade on these engines, these specific IS38 turbochargers specifically. We are singling out this specific turbo because there are many companies, many people, many tuners, many fabricators that offer these as upgrades who are purchasing them from turbocharger specialists, turbo manufacturers, whatever the case might be, and they are not lasting, they are failing. We spoke about it briefly yesterday as to how to achieve a certain horsepower out of a certain size, design, boost, flow rate compressor wheel. Now, if you don't know all that information, watch the video, which I'll put down in the link below or in the actual description below. Watch that and then come back here. So in front of me, I have a failed turbocharger, which you can see over here. This is a hybrid built. I won't mention the company's name. It is not a local company before the guys jump onto the bandwagon and start freaking out. This is a upgrade here, which has failed, and I'm going to go into how it failed, why it failed, factual information, not opinions, and it will basically be off the back of what we spoke about yesterday. So this here, we mentioned yesterday, is a TD06 turbine wheel, okay? Turbine head, not wheel. This shaft attached to this TD06 turbine is not the original dimension, specification, length, diameter, etc. TD06 version. We'll get into that just now. Here is the oversized, and I say oversized because let's do a comparison. That is the standard turbine on an IS38 from IHI. Have a look at that. A little bit closer. There are the two X-juicers next to each other. These two blades are, this is made to look absolutely minute in the shadow of this wheel. If you have a look at the height of this wheel, if you have a look at the diameters, inducer, X-juicer, the X-juicer is 12 millimeters wider than this. And in standard format, everybody knows that as soon as you exceed a certain boost pressure on the standard rotating assembly on your IS38s, your shaft will break over there where your air oil separator groove sits. The first groove is your splits your ring groove. The second groove is your air oil separator. That's where the shaft turns off in standard OEM format as soon as you reach a certain boost pressure. And we're not even talking high boost pressures. This is a known problem. Now the guys go and either upgrade just the compressor, and these are the two geysers that are the most popularly used. 68mm exjuicer, 52.5mm inducer. That there will never last. The thrust loading from the compressor easily overpowers the thrust loading in comparison on the opposite side of the rotating assembly from the turbine, and it will eat your thrust assembly. Now, what the guys have done is said, okay, let's go and upgrade both the turbine diameter and the compressor diameter. So if you have a look at that rotating assembly, diameter for diameter, inducer on the turbine, which is the wider section, exjuicer on the compressor, they are pretty well matched if you look at the outside diameter. Problem number one, the shaft is not a TD06 shaft. This shaft is exactly the same as the original shaft. Now, obviously it is, because how on earth are they going to get this rotating assembly to fit into the standard bearing housing utilizing the original bearing system? They will not be able to, unless they redesign the turbocharger from the ground up, which would cost too much money and it would no longer be profitable. So they go and build, this is obviously manufactured in China because you can't get this turbocharger or this turbine wheel with this guys. IS38 from there to there, TD06 shaft from, in terms of just the turbine head. You can't buy this off the shelf. This is purpose made, and most of the people that make these custom things will originate in Asia. You won't find an American company making low volumes of these. You won't find companies in Japan making low volumes. They would want massive volumes, and the volumes just won't justify a couple of 10,000 or whatever the case is to justify the financial outlay to actually get this done. So the Chinese will basically do smaller volumes, companies like E&E Turbo, and a couple of other companies out there. But at the end of the day, the problem with this rotating assembly exists in the shaft diameter. Let me explain. Here we have a genuine Mitsubishi TD06 compressor wheel which fits a CAT application, irrelevant. The hole diameter, okay, there's the vernier, zero, or caliper as you'd call them in the States. The hole diameter here is 6.48, 6.5 millimeters. Look at the shaft diameter, zero again, on the IS38, 5 millimeters. Let's have a look at the journal bearings next to each other. There's an original TD06, and that is the IS38. Let's have a look at the thrust bearing. Yes, it's upside down, and it's upside down for a reason. And the TD06 thrust bearing. Let's have a look, more importantly, at the collar. There and there. Now, you're using a TD06 turbine and compressor design. You're using a TD06 rotating assembly, and you expect it to be reliable on a tiny minuscule shaft. What do you think happens to the shaft? Yes, it's supported by journal bearings and thrust assemblies, and it's bolted together and it's torqued and this and that and the next thing. What do you think happens to the shaft when the turbine starts to spool and enters a rapid acceleration from, let's say, 0.2, 0.3 bar, and you're boosting this thing 2.5 bar, 2.2 bar, which is where you would need to in order to make the power that this specific compressor and turbine combination are advertised to make. As soon as that rapid acceleration comes into play, the shaft starts to flex because of the thickness of the shaft, because of the lack of ability of these bearings to actually support the shaft inside of the bearing housing. You've got harmonics that come into play, you've got the design of the turbine, you've got the very, very small AR inside the turbine housing, especially when you machine it to use an oversized turbine like the TD06. And obviously, because of the fact that the turbine on the TD06 is so big, the AR inside will actually generate so much back pressure that it starts to cavitate. It starts to find all sorts of vibration issues which make the shaft flexing even worse. Let me explain. Have a look at the compressor wheel. If you come and do a close-up over here, you'll actually see that the compressor has made contact axially with its mating housing. So it started making contact from the tip all the way up the radius profile to approximately there. So these are the two types of play you get: radial play, axial play. We do not have radial play in this specific case because the inducer blades would have made contact with the housing. And if you come and zoom in here, you will find that there's absolutely no contact made between the inducer section of the blades and the housing, yet instead that is where you can see the grind and the damage marks. Now, let's have a look at the turbine. I'm coming to the point now, so just hang in there. No contact, no contact, no contact, no contact, slight contact, more contact, even more, even more, even more. I don't know if you can see that, even more. You can see the shiny contacts over there, and they disappear and no more contact made. But hold on a second, that means the shaft is bent. No, what that means is your thrust has failed. Here are your thrust components. Look at the thrust bearing. Come and zoom in on this. I'll hold it up in the light. You can actually see there's a 1.5 millimeter gouge mark, 1.7 millimeter gouge mark out of a 3.5 millimeter, 3.6 millimeter bearing. Now, that was made by this thrust collar, which you can actually see and hear the grooves. That mates in there like that. That is supposed to have thrust pads which stand level or proud of the surface of this bearing, the thrust bearing. It's been eaten away. Here's how. So people are going to say, yeah, but there's no oil, there's lack of lubrication. Look at the back of the thrust bearing, there's a thermal discoloration. Wrong. If there was lack of lubrication, all the bearings would have made contact, metal to metal contact, and you would have exceeded the thermal loading of the bronze bearing first. Now what happens in that case is, as soon as you heat up a steel shaft, it discolors. There's no discoloration. This is a failure in the presence of lubrication. No shaft discoloration. Yet, there's scoring, okay, there's slight fine particulate contamination inside the oil, but here's the actual crux of the matter. As soon as you get shaft flex, I'm going to use a bigger bearing to illustrate this. This specific collar mates against those thrust pads on that bearing. As soon as you get shaft flex, you no longer have a full surface contact to distribute the load across all of the thrust pads on the thrust bearing. So what you have is you have a very small, this is an exaggeration, a very small contact area making and distributing its load, axial thrust load, onto a very small receiving or recipient area on the thrust bearing. And obviously this component turns, this component remains still. Okay, that's why you have these three holes, because there are actual screws that bolt this down so that it cannot turn. This collar over here rotates on the thrust pads. So back to this example. You know, I have these two faces which now make very, very small aerial contact with one another, area contact with one another, and all of that load is now distributed through a very, very small area which concentrates that. Now, that excessive thrusting from the oversized rotating assembly, together with the flexing of the shaft, will actually overcome the oil film strength. Now, properties of oil, you have flash points, you have detergent levels, you've got a film strength, etc., etc., etc. Now, the film strength has been overcome, you get metal-to-metal contact, and you get thermal discoloration, as you can see on this collar, and on the back of this thrust bearing. Now that is because by design this is a failure. This is one example of a thrust related failure based on an upgraded rotating assembly, both sides, on the IS38 turbocharger. Talking about upgrades, this is the next most common upgrade. This is an oversized compressor to be used with a standard smaller thrust, lower thrusting turbine. Now have a look at the blades. Compressor wheel faces me, turbine faces you. During operation, that is the direction of rotation. Okay, it's clockwise if you look at the turbine. Carrying on, clockwise rotation. If you look at the compressor, it's anti-clockwise. Okay, the thrust loading from the compressor side is in that direction. The thrust loading from the turbine is in that direction. In the middle, you have a bearing. We've now overpowered the bearing with the compressor. Once again, it's 500 plus horsepower rated. In other words, you need to boost this thing to 2.2, 2.5 bar in order to achieve that horsepower output from the compressor, to the detriment of your thrust bearing. These upgrades are just outside of specification. You cannot expect this kind of upgrade to be reliable. Hence the video we released yesterday about the high horsepower bolt-on applications coming out with ball bearing rotating assemblies that can handle the thrust. Last point, Garrett G25 660. Right, let's do some measuring over here. This compressor, X-juicer, measures 68 mils, and at the extended tips, we are looking at approximately, I'll give you an idea in a second if I can just get these tips to fall inside here, 71.7, 72 mils, okay? Inducer, 42.39, 42.4. Okay, so extended tip, call it 72 mils. Let's just get that again. 72 mils, 71.5, and 52.5. G25 660. These rotating assemblies, antiquated, are rated at approximately 525 horsepower. Don't let marketing fool you. They will not make more than that. The G25 660 is rated at 660 horse, and it makes it. And it measures 54 millimeters and 67 at the X-juicer. At the extended tip, it's approximately 69. So this specific shaft diameter is 6 millimeters. This shaft diameter is 5. This rotating assembly uses ball bearing. This uses a thrust bearing. Get my drift? Enough said on the failures and the unreliability of the hybrids, specifically on this IS38. We do hybrids because a lot of people have asked us, can you build a hybrid for me that's going to be reliable, that I can boost 2 bar boost, that I can boost 2.5 bar boost? Yes, we can, but why would you want to? A compressor, once again, is rated at a certain horsepower from a certain pound per minute of airflow rate. On your lower axis on any compressor map, you'll have flow in kilograms per hour or pounds per minute or CFM or whatever the case is, depending on the manufacturer, and a P to C ratio, a pressure ratio. Boost versus flow. The more flow you want, the more boost you'll have to run, and you obviously have your compressor map with your surge limit and your choke line on the other side with a speed reference. It's a 3-dimensional map. If you're looking for 400 horsepower, you don't have to boost 2 bar to get it. The rotating assembly we would use, which I'll put in another video, or I'll actually put the video on the upgrades that we actually do with our own billet compressors in the link below or the description below, will not exceed 400 to 450 horsepower. Because that is the reliable limit that you'll be able to run at 1.6, 1.7 bar boost to make that power with our combined compressor, which is substantially smaller than these, and still maintain a reliable thrust assembly with your journal bearing turbo. If you want more, go ball bearing. There is no solution for a journal bearing setup unless you use the original shaft dimensions from the TD06, replace the bearing housing or remachine the bearing housing or redesign the bearing housing of the IS38 to suit the thicker shaft. It's the only way you're going to get that right. Shaft flex through rapid acceleration of the turbine or the rotating assembly will always be a problem. Guys, I hope that was informative. I know it's a long video. Have a look. There's other excerpts from the compressor and the turbine housing, which you'll see shortly down below now, or actually after the section now. Hope you enjoyed. Hope it's shed some light on this. No disrespect to the tuners, turbo builders, designers, upgraders out there. This is not a dig at you. This is talking fact about problems that are real in the market. All you need to do is ask yourself one question. Why are there so many hybrids that are unreliable? Because they are boosting too much to achieve the horsepower rating that the rotating assembly is advertised. If you try and run 1.8 plus bar boost gauge pressure, you will find a failure, period. It's that simple. The grass is green, the sky is blue. Lots of people know that's the saying that comes from me. Hope it's been informative. Like, dislike, comment below, subscribe, click on the bell. You guys will be notified of new videos. See you next time. With this IS38, turbocharger, which has basically failed catastrophically, and it utilizes the TD06 shaft, which I've already gone over. But they've obviously taken the standard stainless housing and they've just machined this open for a hugely oversized wheel, specifically in relation to the turbine housing AR. This is a standard original IHI turbine housing which has been machined to accept a derivative of a Mitsubishi TD06 turbine wheel. Now, the ARs on the Mitsubishi turbochargers, or at least the Mitsubishi turbine housings that house the TD06 turbine shafts, are 8 centimeters cubed, 10 centimeters cubed, 12 centimeter cubed as a minimum. The smallest housing you get that will mate to a TD06 rotating assembly, purely because of the back pressure and the efficiency of the turbine, is an 8 centimeter cubed housing. This specific housing from the Golf 7.5R EA888 engine has got a very small AR. If you want to compare it to the Mitsubishi, it's probably about a 4.5 to 5 centimeter cubed AR if you want to do a direct comparison in centimeters cubed. But I can tell you now, the turbine housing back pressure in here with that size rotating assembly is part and parcel of the failure. We'll talk about the compressor stage next. Okay guys, here we are with the compressor housing. I've just taped closed the nameplate of this company. This is a product manufactured, or should I say upgraded, by a specific company which we're not going to reveal. And the turbocharger, or at least the compressor housing, is an original IHI. At least the casting says so. I'd like to just bring to your attention that inside of these housings in standard format for the original wheel, which is substantially smaller than this, you do not have an aluminium casting on your diffuser area over here and the radius profile. There's actually a Bakelite insert that basically sits inside of this radius profile here, which obviously needs to be machined out, broken out, and then the housing needs to be modified so that it can then obviously be machined. And typically what the guys do is they weld them up. Or what they'll do is they'll actually go and machine this entire piece here and press it in as an insert, which seems to have been done in this specific case. But you know, once again, you're redesigning and remanufacturing and modifying the housings. You're always going to find a problem, a potential problem with concentricity. Yes, you can set it up on a lathe and you can set it up on a mill, and you can use a 3-axis or a 5-axis clock gauge, and you can get as close as damn it with the specific type of technique. But what you will always find is, depending on the materials, and if there are differences between the materials metallurgically, this might have a slightly higher or lower expansion rate than the housing itself, and if this insert comes loose, you've got problems. Now, you can obviously see on this specific failure that there's contact made between the radius profile of the compressor wheel and the housing from the exjuicer side moving forward, and then obviously there's not much contact made on the inducer profile of the actual compressor wheel. But this here would require axial or end float, axial movement of the shaft, in order for that part of the profile on the compressor housing to make contact with on the compressor wheel to make contact with this housing. So there is a little bit of a brief on the compressor side. We'll get further into the actual bearing system next. Hey guys, here we're back with the bearing housing. As you can see, the first thing you'll notice is the heat shield is missing. I'll show you where that has landed up in a while. Standard bearing housing from the IS38. It's an IHI product. Nothing has changed internally. None of the structure, none of the dimensions in terms of where the journal bearing runs, the thrust assembly, the thrust components themselves, nothing has changed or been upgraded in the bearing system whatsoever inside of this bearing housing.